is flat. If I were to introduce gravity theory in the standard model, what would I do? I would first introduce the curved space-time manifold. As you might have heard or read this line at many places, that gravity is the manifestation of the curvature of space-time. So space-time has to be made curved, okay? Which means the metric tensor which we talked last week. So instead of having value plus 1, minus 1, minus 1, minus 1, or minus 1, plus 1, plus 1, plus 1, maybe it has some A, B, C, D, which are functions of x mu, which means they are fields. So G mu nu metric tensor, eta mu nu, which was flat, was not a field, it was fixed, it was constant, its value was either plus 1 or minus 1. But now with the Lorentz signature in Minkowski space, space and time have to differ by one minus sign. If we make them some variables which are functions of x, y, z and t, then they are all fields, they are gravitational fields called metric functions. And the metric tensor G mu nu, the generalization of eta mu nu, which was fixed, G mu nu itself is a function of x mu. And now, if you are successful in writing down such a theory, it would be invariant under the general, what is that called?
Local vector?
General coordinate transformations. General coordinate transformations, which is where your G mu nu, the metric field, which is the gravitational field itself, it also transforms according to these transformations. Okay? So, now what about gravity? What is so important about gravity? Gravity happens to be one of the most well-known theory. If we go to a farm, आप एक कहीं पेड़ के नीचे भी बैठे हैं तो एप्पल भी नीचे गिरेगा लेकिन मैंगो भी नीचे गिरेगा. So it makes you worry that there is some gravitational force which we now know. I cannot go too much into more elementary things, otherwise my story will continue up to 10 p.m. and you people would be detained here. We have to spend, Girma ma'am will have to provide us some food, right? So now gravity theory works at large distances. It explains the physics of cosmos. And let me highlight the importance of these things. A well-noted physicist or an interplanetary scientist, Carl Sagan, mentions in his book Cosmos, very celebrated book. He died at the age of 40 or something. He wrote many books. One of them was Cosmos. You can Google it out. He says that Indian ancient literature or Indian ancient religion, or if you like, you can call it Sanatan, if you don't object to it. I personally like to call it. I'm not even calling it Hindu. I'm calling it Sanatan. It's something which is true has been true for a long time. So that in the Sanatan cosmology or our Hindu thought, as mentioned in Rig Veda and Bhagavad Gita itself, that universe itself, or one should not even call universe, the cosmos, themselves go through an infinite series of cycle of deaths and rebirths. This is what our Vedic cosmology tells us. Please do try to look at these concepts somehow. You can find them out. You are smarter than old-fashioned people like me. Yes, it will come out to be true. It does talk about it. And you might have heard about the one day and one night of Brahma. This is something like 7 to 8 billion years. So this Vedic cosmology talks about the time scales, which are cosmological time scales. The universe was born something like 13.7 billion years ago, this so-called Big Bang theory. And all the fundamental forces of nature, they were also born right at that time. And we have been trying to learn, I mean, after how many billion years, these systems like solar systems, planets and so on came into existence, then humans came into existence and so on. Please have a look at all these things. So we are fortunate that we are living in the intelligent times. And so if you are willing to accept the modern cosmological scales, like 13.7 billion years ago the universe was born, then just half of it corresponds to 1 day or 1 night of Brahma, which is 7 to 8 billion years. So you should look at the concepts, cosmological scales of times. They match so perfectly. Then a few things about gravity theory. I may have mentioned it earlier in some other context, but it may be nice to recap that the escape velocity of a particle of mass m put on some object of radius r is given by square root of 2 mg by r. This we do in 11th level, school level. So if I have my earth and I throw a particle, if its velocity is less than the escape velocity, it falls back on earth. Now what I do, I want to keep the mass of the earth fixed and I want to reduce the radius. I keep it reducing till the radius of earth becomes 8.43 millimeter. Then this escape velocity becomes identically equal to the velocity of light. What does it mean? Even if I throw away a photon from earth, I want it to escape the earth's gravity, but it falls back on earth. It does not go out. So a black hole is defined as an object from which nothing can escape, not even light. So then in that position, my earth has become a black hole. If I do a similar calculation for sun, it would be something like 3 kilometers. If I squeeze my sun, keeping its mass fixed into a radius, a small spherical ball of radius 3 kilometers, the sun would become black. Now look, during the last 10, 12 years or so, there have been huge progress in this direction. The detection of gravitational waves at LIGO, you must have read in the newspapers, right, some 10, 11, 12 years ago. Then mapping of the black hole image. We live in the so-called Milky Way galaxy, our own galaxy, Milky Way galaxy. There is a distant galaxy called as M87. There is a super massive black hole sitting at the center of that galaxy, M87. This supermassive black hole has something like 40 billion kilometers radius or diameter spread. It's larger than the size of our own solar system. You see? And we have the so-called Event Horizon Telescope. You might have heard of this name. It was in the newspapers, magazines, patrikaon mein. Event Horizon Telescope, EHT. You write in the Google and you find. So it's an array of 8 telescopes spread over the entire surface of the earth in different countries. They are located. And this is a very beautiful, very fascinating thing. So they were able to map the image of this guy, this supermassive black hole sitting there at the center of M87 through this Event Horizon Telescope. Now, the Nobel laureates of 2020, Mr. Roger Penrose, he has been to India a couple of times. I at least talked to him twice in New Delhi. He predicted, or you can say general relativity predicts, that even our own Milky Way galaxy has a supermassive black hole sitting at the center of this, our Milky Way galaxy. And this location is known by the name Sagittarius A star or SGR A star at this location. Now, if it is so massive, what happens? Thousands and hundreds, thousands of objects would revolve around it. Now, there is a physicist, woman physicist. Also, she shared a Nobel Prize along with Roger Penrose, along with one more, Reinhard Ganser. These three guys, they shared the Nobel Prize. This woman physicist, she tracked, she first decided one event, one particular object known by the name SO2 or S2 star, which revolves around this supermassive black hole sitting at Sagittarius A star. And its period of revolution is something like 16 years, little more than 16 years. So this woman physicist was brave. She kept tracking the orbit of this guy, S2 or SO2, for more than 16 years. She made it to a Nobel Prize. Only 4 women physicists making it to a Nobel Prize in physics. She is one of them, so it's a very rare thing. And look at her achievements. Now, there is one thing called as Perihelion Advance. Perihelion Advance of Earth, Perihelion Advance of Mercury. So, Earth is revolving around the Sun and it takes 365 days. Then Earth comes back at its position. You consider the major axis of this Earth, and what happens in 365 days, this major axis gets slightly rotated. So the Earth does not come back to its original position this way or this way, it gets slightly rotated. This is called an advance of perihelion of Earth. It's a very, 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 very tiny fraction. But Mercury, Buddha in Hindi, the nearest star, nearest planet to our Sun, it revolves around, it makes one revolution around Sun in 88 days. And its elliptical orbit